Welcome to lecture 33. In this lecture, I want to talk about black hole thermodynamics. Recall that in the preceding lectures, we discussed black hole physics. In particular, we used Hawking's original calculation to calculate the temperature of a black hole back in lecture 32. In this lecture, we want to extend that relation between black holes and statistical mechanics by considering what's known as black hole thermodynamics. To get started, recall that in the last lecture, we found that for a black hole of mass m, the black hole will emit radiation that will have a temperature T that's given as 1 over 8 pi g times the mass m. In ordinary thermodynamics, there are relations between thermodynamic quantity, such as energy, entropy, pressure, and so on. In the lecture at hand, what we want to do is we want to figure out how these relations look like for black holes. So just recalling a few basic thermodynamic relations from your statistical mechanics course might be useful. Recall that in thermodynamics, this is a classical description of your system at a finite temperature T in a volume V. If you consider thermodynamics, there are quantities such as the energy, the pressure P, the entropy S, that are related by thermodynamic relations. An example for a thermodynamic relation is the relation between the entropy S and the derivative of the pressure P at fixed volume. So S, the entropy S, is given by dP dt, the derivative with respect to temperature, times the volume of the system V. Another thermodynamic relation is the relation between the energy in the system and the entropy S and the pressure and the temperature and the volume, which is given by equation 33.3. And finally, you can derive other thermodynamic relations, for instance, from these two, such as the relation dE is TdS, where D just stands for any derivative. And you can prove this relation here by sort of using these two relations as inputs. So thermodynamic relations can be transformed into each other, starting from a few basic sets. Okay, so now let's try to apply thermodynamics to black holes. The first thing I want to concentrate on is the energy of a black hole. That's fairly easy because in general relativity, mass and energy are the same thing except for a vector of c squared, which is 1 in our units. So that means the energy of a black hole is just the mass of the black hole if the black hole is not moving, which for our Schwarzschild black hole is the case. So because the energy and the mass of the black hole are the same, we can try to derive some thermodynamic relations that go beyond the energy of a black hole. For instance, we might aim to calculate the entropy of a black hole. To do so, we do a derivative of the energy, which is then a derivative of the mass, and use the basic thermodynamic relation to relate dE to the entropy. So the basic thermodynamic relation tells us that dE has to be equal to TdS. So that means that TdS of a black hole is equal to dm. Now we actually know the temperature of the black hole in terms of the mass of the black hole. This is just the Hawking temperature given in equation 33.1 of the present lecture. If you plug this in, then we find that the change in entropy, ds, is equal to the inverse temperature, 8 pi gm times dm. Now we can integrate both sides of this equation and find the relation for the black hole entropy. The entropy of a black hole is given by 4 pi g times the mass of the black hole squared. So that's one result, but it is getting more interesting if we compare this result to another quantity, namely just the area of a black hole. So again, this is fairly easy to calculate. You start by taking the Schwarzschild metric, which is spherically symmetric. The black hole has a horizon radius that's given by the Schwarzschild radius Rs, which is just 2 gm. So if you have a sphere with radius Rs, you can calculate its area. The area of the black hole is just 4 pi times the radius squared, but the radius is now the Schwarzschild radius. Plug in Rs, and you find that this area is 4 pi times 4 g squared m squared, or it's just 16 pi g squared m squared. So we have that the area is 16 pi g squared m squared, and the entropy is also a constant times m squared. So we find that up to a constant factor, the area and the entropy of a black hole are the same. This gives the relation that the entropy of a black hole is given by the area of the black hole divided by 4g. This relation is the so-called Bekenstein-Hawking formula for the entropy of a black hole, which says that whenever you want to calculate the entropy of a black hole, you just need to look at its area and divide by 4g. That gives a very straightforward way to calculating the entropy of a black hole. Now, you might say that, okay, that's weird. You have an entropy of a black hole. What does it mean? It means something because we found that there is this sort of set of thermodynamic relations which we now can bring to bear on things like the properties of the black hole. An example of this are the so-called area theorems that I want to talk about now. So we find that the area of a black hole is proportional, or the entropy of a black hole is proportional to its area. And we also know from classical thermodynamics that the entropy in any process has to monotonically increase. So that means that any change in the entropy has to be always bigger or equal to 0. So this involves non-equilibrium processes. So in particular, if we want to perturb the black hole, or if we want to perturb statistical mechanic system, its entropy always has to increase. Because now we found this relation between the entropy and the area of the black hole. And if we furthermore assume that this is more than just a mathematical curiosity, this means that the area of the black hole also has to fulfill a law like this. It just says that the area of the black hole also always has to monotonically increase. This is the so-called area theorem of black holes. If you take a black hole and you perturb it in whichever way possible within GR, then its area has to increase because of basic thermodynamic relations. And this is a very powerful statement saying that you can't really decrease the area of a black hole, at least within classical physics. Classical physics, because also the second law of thermodynamics is a classical law, and it can be violated by quantum processes. As a consequence of the area theorem, we find that if we think about more complicated things, such as black hole collisions, there is a relation, an inequality between the total area of the final black hole after these two black holes have collided and the initial areas of the incoming black holes. Basically, the area of the final black hole has to be bigger or equal to the sum of the area of the incoming black holes. Now, this is an important statement because it basically sort of says that because the area sort of is proportional to the entropy of the black hole, that also means that it's proportional to the final mass of the black hole. So this gives a limit of how heavy sort of the final black hole has to be. And because energy is conserved in the whole process, this also means that this puts a limit to the amount of entropy or energy that can escape, for instance, in the black hole merger process. And as such, it limits the amount of gravitational waves that can be emitted in such a process. In some cases, if we, for instance, assume that this is an equality or something like this, you can even put estimates on the amount of gravitational waves that can be produced in such a process. Of course, the loophole to this argument is, again, that it is a classical statement. So there are quantum processes that can potentially violate the area theorems. An example of such a quantum process is indeed Hawking radiation, because it's a quantum process. And how these things hang together, so how quantum black holes, if we want so, really evade the second law of thermodynamics is something that's known as the information puzzle. The information puzzle is something that's not really solved in GR, and it is a subject of current research that extends way beyond classical general relativity into string theory, quantum information science, and it's a sort of big research area at the moment. This concludes the presentation.